SEV transports the people with mobility restrictions with the bending of fingers. We do this by detecting the strain on the fingers with the strain gauge. The cantilever bending simulates the bending motion of the fingers. The bending of the forward cantilever results in a forward motion, and the bending of the steering cantilever results in a steering. SEV is divided into 4 sections. 1. Obtaining the bending information via strain gauge. 2. Using the Wheatstone bridge and op-amp to record the voltage input via DAC. 3. Using LabVIEW to interpret this input and sending appropriate signal through DAC for driving the SEV. And 4. Taking the signal in the motor circuit to produce appropriate PWM output to run the motor.
Strain gauge works by measuring the strain being applied as a change in electrical resistance. Under tension, the resistant output increases. Under compression, the resistance decreases. Strain gauge was used to detect the force being applied on the cantilever to drive our motors. Using the calibration curves produced from testing, we divided the bridge output into no press, slight press, and strong bending.
The second part is using the Wheatstone bridge and op-amp to record the voltage input via DAC. The Wheatstone bridge circuit takes in the change in resistance from the strain gauges and outputs a voltage. This voltage is amplified using a differential op-amp by a gain of 225. As we anticipated an input range of 0 to 10 millivolts, it was necessary to amplify our signal to make more use of the plus-minus 10 volt input range. The third step is using LabVIEW to interpret this input and send the appropriate signal through the DAC for driving the SEV. Our LabVIEW program incorporates a low-pass filter and multiple if statements to send the appropriate output signals to the motor. When the program reads any negative deflection in beam 1, it writes to the analog output channel 1 of the DAC to send 5.28 volts to the forward motor circuit. When a small bend in beam 2 is read within -100 and -500 millivolts, the program writes to analog output channel 0 of the DAC and sends 5.14 volts to the steering motor circuit. When there is a large bend, less than -500 millivolts, 5.2 volts is sent to the same circuit to turn the motor the opposite way.
The last part is taking the signal in the motor circuit to produce appropriate PWM output to run the motor. Our motor MG996R required a PWM signal to operate. In order to convert our voltage output from the DAC to a PWM signal, we use a customized motor circuit as follows. The 2 op-amps labeled in red produce a triangular wave of signals. The blue op-amp shown in the circuit diagram takes in the triangular signal and the DC output from the DAC, shown in yellow, to produce an on-off signal. As shown in the diagram, the positive difference between the yellow and red produce a peak. The negative difference between the yellow and red produces a null signal. This on-off signal, also known as the PWM signal, runs the motor at different capacity based on the width of each bar. By increasing or decreasing the DC voltage, we are able to change the width of the PWM signal.
Now let's take a look at the demo.